hand in your proposal if that is your plan. Any questions about the proposal and about the projects? So there's also going to be 2 milestones, and in your first milestone you should have essentially done your data collection, and you should have one of your views up, and you should have like a working prototype of your visualization. This is really, we found when we ran this class with just one submission for the final project, the results were much worse than when we do it with 2 milestones, because there's 2 things, right? You have spent more time on it, and we have a chance to give you feedback. And so the more involved you are with your TA, the better. And then right after the project proposal deadline, there will also be a peer feedback session in class at class time, where every team has to participate. We'll be taking attendance for that. And what you do there is you take 30 minutes and pitch your project to a peer. They give you feedback. And then we flip roles. Then the other team pitches their project, and then you give feedback. And there will also be like mandatory formalized meetings with your TAs, but we'll announce this after fall break. So any other questions about the project? Great. Next week on Tuesday, Carolina will again be teaching about D3 layouts and a couple of other D3 utilities, for example, how to do linking and brushing and how to filter D3 selections. And then on Thursday, I'll be teaching about designing visualization and tasks. And for that, we will be doing another mandatory reading, this nested model for visualization, design, and validation by Tamara Manzner. This is also the same person who wrote our mandatory textbook. And just as a reminder, I actually made a slight modification to what I said previously here. These papers, the nested model, this one today, and the hair paper about crowdsourcing, they're subject to be tested, but only for 6630 students. So the undergrads don't actually have to answer questions that are not covered in lecture, but for every grad student in here, I can ask anything that is in this paper. So D3 papers, you really have to read them. I'm not going to ask like stupid questions, right? I'm going to ask things that are kind of central to the paper. I'm not going to ask some tangent that the authors talk about in the related work. But you should definitely, like, every grad student has to have read those papers before coming to the midterm. Okay. So, anything else organizational that anybody wants to talk about? Great. So, interaction. So there is a spectrum of interactivity in how we talk about visualizations. On the one side, there's static content. So whenever you have a printout, a newspaper, or very many infographics even on the web, or books, then you have a static visualization where you can't really change anything dynamically. And then we have dynamic content. And there is a distinction between animated content and interactive content. So if you remember in the introductory lecture, I gave this example of this baseball pitcher who essentially was a really good pitcher. That was a video and it used dynamic visualization, but it was completely animated, so there was no user interaction in there. What we are mostly interested in the rest of this course is the interactive content, where changes are the result of direct user actions. So why do we want to interact with visualizations? Well, there's 2 main reasons. One of them is that we want to explore data that is simply too big or too complex to show in one single plot, to show without any interaction. So there's either too much data or there are too many ways to show it. And so we have seen this example before here. But, so what are the interactive parts here? There's 2 main interactive parts. There's the tooltip, which kind of reveals additional information about those circles, about those companies. This would be really, like, this is a lot of information that we simply wouldn't be able to show efficiently for every single node on this list, right? And then the other way to interact with this tool is to split it up by a different attribute. Like, I can click here and then I see something that I didn't see before. I'm kind of like using interaction to show me, like, 1, get an overall context, and then 2, break it down by industries. And so this is a good example of how you can use interactivity to simplify a data set and to show something that you could otherwise not easily. Interaction also amplifies cognition. Like, this is also like, when we do something and play with something, we understand them better. So this is really like a great effect for learning. So here, I'll be coming back to this example when we do multidimensional data visualization. But this here is just a visualization of how principal component analysis works. And so principal component analysis finds the dominant, essentially, direction in a data set. And so here's a two-dimensional data set. And that is the output of the PCA. I have in the first principal component, I can see that I capture all of the variation that I have on this axis. But why am I showing you this? Because here I can now interact with this visualization, right? I can move those points around and I can immediately see how moving these points affects the outcome of the PCA. And by using this interactive feature here, I can actually start to get a better sense of what is a principal component, what does the principal component analysis do, right? And this is really the second main component about interactivity, that it augments our cognition. There are many interaction methods, and we can design for different ones. And so, like the standard ones that we've been using in a professional environment for many years now is mouse and keyboard. But of course, more important in recent years is touch interaction, and especially on the mobile phone. What about gestures? Like, who thinks that gestures are the future of human-computer interaction? Okay, a couple of people. Who thinks that speech is the future of human-computer interaction? A couple of people. You guys, nobody here shares an office, right? It would be really tricky to have a grad student lab and everybody just interacts with their computer using speech. And also touch interaction has a couple of, gestures have a couple of interesting drawbacks. I'm going to show a video about this in a second. What about eye movement? Could I augment my selection? Like, anybody have an idea? How can I use eye movement? You want to say something, or? So, eye movement is, I've actually played with this myself. I tried to use eye movement to let people select something or to show details about an item that you're looking at. The problem that you have with eye movement is what's called the Midas touch problem. Eye movement is not voluntarily. I cannot make a distinction between I want to look there and click, or I just look there because I need to look somewhere and I need to move my gaze quickly. And so I wanted to show this video because I think it makes a really good point, especially about gesture interfaces.
Hi, I'm Alice Kaufman. I'm an interaction researcher, which means that I explore and prototype future uses of technology as a way of understanding the future. And I really, really hate Tom Cruise. I specifically hate Minority Report Tom Cruise. With his perfect haircut and his power stance, chopping at the air to sort of scroll through scenes of crimes that haven't happened yet, because it has conditioned us to expect that the future of gesture interfaces is going to look dramatic. All the gesture tech we're building, the Leaps, the Connects, the Mayos, they all demand these highly visible gestures that are distracting us from a more pedestrian, less cinematic future that is definitely more usable than this. I mean, every time I see this scene, I think, Tom, you're standing 2 feet away from the screen. Why don't you touch it? He's replaced direct manipulation, which our hands are really good at, with this kind of elaborate sign language, which our hands are really bad at. It's as if I said, like, it's the difference between solving a Rubik's Cube and explaining to somebody how to solve it by pointing. And the thing is, our hands are very coordinated. I mean, you can be walking down the street and pick up a penny without breaking your stride. But unless you're a mime or a dancer, you're going to have a really hard time pointing at the same spot in space twice in a row. And anybody who's ever used a Wiimote knows it's really hard to point precisely. But I think there's a feeling among people that somehow getting rid of a controller makes an interaction feel more natural. And people have become so obsessed with this idea of getting rid of the mouse and replacing it with gestures that they've actually forgotten how we use our hands. Because most of the time, we're not gesturing. In fact, 90% of gestures occur when we're speaking. And studies have shown that all of those gestures, almost to the last one, are for the benefit of the speaker. They help the speaker keep track of what he is saying. They convey no useful information to the audience. Now, I'm not saying that we can't use gestures and interfaces. What I'm saying is that we've got to pay attention to what their unique characteristics are. They're fast, they're silent, they can be performed at sort of any variety of distances, and most importantly, they have this kind of inherent directionality. So at least in theory, you could use gestures as this kind of meta-unifying input across a series of devices. And what I mean by this is, for instance, if I point at my stereo and it turns on, and then I point at it and it turns off, and then I point at my TV and it turns on, and I point at my TV and it turns off, I've actually established a common language that both of these devices understand. And I can use this language as a way to connect them in a way, in a very intuitive way. So, for instance, if I point at both my TV and my stereo, if the TV is on, it pipes the sound to the stereo. Or if the stereo is on, it actually pipes the music video of the song that was playing or the album art. This all sort of presumes that gestures are these explicit and very deliberate motions. And I think actually the real magic happens when the applications start to pay attention to what we do with our bodies normally, what we do with our hands normally. Because once machines can interpret our normal motions, they can find some insight into our intentions. And machines that understand intentions can actually start to help us. So for instance...
So yeah, I want to stop here, but I really like this point that he's making. The most promising approach for gesture-based interaction, except for some niche use cases, is when they're not intrusive, when they are natural. Like learning commands on a Wii or how to navigate a menu is simply not something that is usable, and it's also like very strenuous, right? You don't want to use your office computer 8 hours a day by waving your hands around. So he also mentioned this concept of direct manipulation, and we use this same idea. This is like a broad human-computer interaction idea, but we use it a lot in visualization too. And direct manipulation is a really important visualization and user interface concept, and it has been shown to be a very effective way of interacting with data visualizations. So what is direct manipulation? It's really about interacting directly with an object and getting continuous feedback and updates. And that, compare that to like using a query or using a slider somewhere else. And so here is a good example for that. This is a scatterplot matrix. We'll be talking more about this. But here I'm creating a brush. And I'm not defining somewhere like brush this first 2 dimensions in the range of whatever 7.0 and 5.5. But I'm actually just like saying and doing what I want to do. I'm directly operating on the filter or on the highlight that I want to, and I move it around as I want it to happen. And we'll see interfaces later today where this is not the case, where we have these indirect ways of manipulating things and interactions. But usually, whenever you can, a direct manipulation doesn't work for every use case, but whenever you can, try to use direct manipulation in your interfaces. So there's a couple of types of interaction that I kind of like will be using to structure the rest of this lecture on. I distinguish between single view interaction and multiple view interaction. And so we'll be talking about how to visualize change over time, or how to use interaction for change over time, how to navigate, how to semantically zoom, how to filter and query, and how to do focus and context. And then we'll have it's not actually the next lecture, but we'll have a lecture after fall break on view coordination, where we will be talking more about interaction as it pertains to selections for details on demand, to linking and brushing, and to adapting representations. Okay, so now let's talk a little bit about this paper. Who wants to give us a brief summary of what this paper is about? Yeah.
Super brief summary was talking about this is up there, taxonomy of interactive elements, and so it's sort of different ways that you could go through and plan out your data to kind of explore it or analyze it in different ways, as opposed to just looking at a single screen, and that's all you get.
Yeah, and so did you, like, was this all intuitive to you, or were there some new concepts that you didn't think about so much in terms of interaction? Or anybody here?
Yes, I would say that I thought the idea that when you're selecting different elements, that would bring up different views and like narrow in on the data was really cool. I hadn't really considered that.
Okay, and so did anybody think of these provenance and process aspects ever before as an interaction modality? I think this is like a very special case, right? And so this paper really gives you a kind of a good structure of what are the different types of interactions. So maybe let's go about them. Like, what is the purpose of the data and view specification interaction? So what do I want to do in that class of interactions? Like, the basic thing that I want to do is I want to define which data sets do I want to visualize and how do I want to visualize it, right? So this is kind of like the very first element. And in many cases, this has already been taken care of. If you go to a New York Times website, we don't actually have to say, I want to visualize this data set and I want to use this visual encoding. This decision has been made by somebody else. But if I had like a visualization system like Tableau, this would be Tableau is off the shelf, or Excel. This would be the first step. Like, I select the data set and I choose which visual representation to use. Okay, what is the second one here? Can somebody give an example?
You want to make whatever you're looking at relevant to what you're interested in, so you want to filter stuff out.
Exactly. I very often have a massive data set, and I want to remove the items that I'm not interested in just to make it easier. What is related to that? We have sorting. Why do I care about sorting?
So that we can compare.
Yeah, so that we can compare, but what does sorting also allow us to do?
See the trend.
Exactly. See a trend, quickly reveal the biggest or the smallest item. So all of these questions can be answered with sorting. I'm going to skip over the coordination aspects because we're not going to be talking too much about them today. And for the process and provenance, like, has anybody ever used the visualization technique that allowed them to annotate that? Like what they found? How would you usually, let's say you write a paper about something, you have a finding and you create a bar chart in Excel. How would you go about annotating that?
Putting labels on the bar chart.
Yeah, you could put labels on the bar chart, you could like put it into Illustrator and draw a frame around one of the bars.
You also like color something so that it draws attention to that and away from other things.
Exactly. And so most visualization techniques and most visualization tools here are not particularly good about supporting these classes of provenance. So what is actually, does everybody know what provenance is? Like, does anybody want to define provenance for me? And how does it materialize in a visualization system? So provenance is the history of an item. So this is like used, for example, in the art world. The provenance of a piece of art is who were the owners of this art piece, who owned it, where was it stored, and so on over its history. Which is, of course, important if you have events like wars. Like, for example, when a lot of Jewish, like art owned by Jewish people was stolen by the Nazis, there's like a big sector in art history that tries to understand the provenance of these artworks and give it back to the rightful owners. And so how do we use this in visualization? Like, yeah.
So I would say if you were like narrowing down different sets of data, understanding when you're at a particular step, where you came from,
Yes.
Is important for context.
Yes, and so it's important for context, but what is the most basic provenance operation? Like which you probably, everybody here uses all the time, not necessarily in a visualization context, it's undo, right? Undo and redo, like this undo and redo stack is what you can actually do by capturing the provenance. If you write code, you have the provenance of the text, how in the sequence that you have written it, and you can do undo and redo up to a certain point usually. And then there's these other things here. Annotate patterns to document findings, share views to enable collaboration, and guide user through analysis, tasks, or stories. And so I kind of wanted to show you a couple of examples here. These are not links. So here is a table visualization. This is actually like a prototype that me and a couple of collaborators are working on right now, but it has a couple of neat things. So if we look at this table, we can cover many of the different aspects. So for example, I want to specify a data set. So I can say like this is an AIDS data set, and I can say, okay, let's add a new data set. And now I have added this data set. So this is the data and view specification by visualizing the data by choosing the visual encodings. Then I can actually here change the visual encoding that I use. So I can either show it as a bar, or I can use it as a circle, or I can just show the text value, or I can use it with like a brightness value. Then I can filter out items. So here, this is like an AIDS data set, so I could remove all of the Asian countries here. Now I have like deselected this, and now I've deselected all of the European countries. And so you can see that in the histogram up here, those have disappeared. Now, if I wanted to sort, I could simply click on the header here, and then I would get this sorted by continent. Now the next thing is deriving, right? If I want to derive a data value, I can do here an operation where I simply say group this, and now I have all of the African countries, and then I can summarize all of the African, all of the American, all of the Oceania, and all of the South American countries. And now I have this very abstract representation of this big data set, and I only show derived data sets, right? I have used one variable to derive something else from it. So this would cover all of the data and view specification examples. And then of course I can also select. So we have this implicit selection here. This is a little bit more interesting if I try a more compact visualization here where I fit more items and therefore kind of have less space to show them individually. And so what I do here is by selecting these items, I can actually reveal what these items are. So I can I get an overview of everything, but by selecting them, I can see the details about individual items. I'm going to skip over coordinate and organize again, because those are concepts that we'll be talking about in the view lecture. And then, as I mentioned, there is also this, many visualization techniques don't support provenance. Provenance tracking, many visualization techniques don't support any kind of history, especially academic tools. But here is an example that covers many of the bases down here. So the first thing is that we have the record button. So here this is like a scatter plot of some human development data. This is GDP for different countries plotted against the life expectancy at birth. So we can see that, and then we have different, we have time down here on an axis. So we can see in 1800s it was quite different than somewhere around 2010. But what you will notice here is that when I interact, like let's say I click on something here, everything here is logged. This, you can see that here, country India was added. Now if I click on this one here, I'm adding Russia. And if I click on this one here, I'm adding China. So this logs everything. And I can jump back into any of those states. Like I can jump back at this to this very beginning. So I have a complete record of what I've done, and I can revisit it. I can even branch off, like here's a branch of where I have diverged in an analysis. And then I can annotate. So to annotate here, I would say let's pick this, there is a separate mode here for authoring, and I could say let's add the current state to build it into the story. So now I've added the currently selected China to this story. Okay, and now I could do an annotation. Like I could say, here is an arrow. And then I can add the text label. You can see. Something about that and position it. And now I can actually switch to this share and guide mode. So here, if I go to like this presentation mode, I can like play through a curated story dynamically and then show individual items as they were curated by an author. And I have different annotations in here with different highlights and selections and so on. And so this is a way to share, like this is also stored on a server, and so I can easily send it to somebody else to like revisit my story, but I also have this guidance, and I can even automatically play this without any user interaction. So this is essentially just to illustrate what Schneiderman and Hare mean by these different terms, and we'll be talking more about the view-specific ones later. Okay, so let's talk a little bit more in detail about change over time and transitions. So change over time, for example, you could use a slider to see views with data at different times. But sometimes it's better to show the difference explicitly. So does anybody remember an example that I gave last lecture where this was the case, where we had temporal data and we discussed the difference between showing everything at the same time and showing everything in animation? It was the fertility rates, right? We had fertility rates in Japan and the US over a long period of time, and we talked about how we can use this. But here I want to show you a simple example. This was actually a class project. In this class, this showed you the growth of a nation. Essentially, I'm making a point, telling a story about how the railroad, the building of the railroads influenced the growth of the country. And so this is like a really good example because it has multiple views, and it has like you can either slide the years here manually. So you can see now this is like now increasingly many states, and then we see the first railroads appearing here in the northeast, and then sometime after that the railroad network extends, and then it suddenly connects the east and the west coast. And so here I do this direct manipulation, or not direct manipulation, because this is actually indirect manipulation. But I simply choose the year, but I could also just say, play this automatically, show me an animation. And this kind of gives you a good overview of how the states have grown. Of course, it's way too little time here to read the story here. Change over time doesn't have to be literal time. It can be also change as you go as part of the analysis process. So for example, this is a technique that I'll be talking more about when we talk about tabular data visualization. But I can change, like here I'm changing weights, or by simply changing a parameter in the GDP visualization that I showed earlier, I do make changes over time as part of the analysis process. And when you make these changes to a visualization interface, you always have to think about whether you want to do some dynamic transitions or whether you want to completely refresh your view. So here this is like a nice example for transitions. It's not that important what this is genomic data, but here we have a couple of different visual representations, and we can switch between them and have these nice transitions between them. So 2D with even spacing, 2D quantitative, then 3D, with another data added on top, and then recombination rate, this other data set from top. So we have these like different perspectives, and we have these transitions between them very neatly implemented. Or here I could, like similar to what we've seen in the other interface, I could simply change the ordering dynamically. And then here we show transitions. So what would be the problem of changing like orders like that? Do you think this is always a good idea? So what happens if I have too many items in my rows? So let's say I'm adding, like this is now a pretty big data set. I have a lot of rows here. And so if I start sorting, like doing this we actually switched it off here. But if I were to do the sorting with the dynamic transitions, it wouldn't mean much because I'm actually not seeing most of the data on the screen. So the target and the target positions are very often off screen. And so that doesn't make much sense. And so people have actually studied conditions under which transitions make sense. We've seen this a lot in D3. We've talked about transitions. Here's a nice example of a sunburst visualization technique. And here is in the transition between stacked to grouped bars in D3. And the point of these transitions is essentially that people can keep track of what is going on, right? But there are limits to that. And these limits, they have been studied, and this video briefly introduces this.
When analyzing or presenting information using statistical data graphics, it is common to look at a number of related graphs. For example, the viewer of a bar chart may want to switch to a pie chart to view relative percentages, transition to a scatter plot to look for correlations between two variables, or drill down by breaking up the data by categories. Animation is one promising approach for facilitating perception of changes when transitioning between data graphics. Using design guidelines motivated by research of human perception, we have developed Dynaviz, a system supporting animated transitions for statistical data graphics. Dynaviz provides animations for a number of different transition types, including changes of perspective, filtering operations, and viewing changes of data over time. In some cases, changes of value require changing the axis scales. Here we show a sorting operation. Animating everything at once can result in items occluding each other. By slightly staggering the movement of each of the bars, Dynaviz makes the sort easier to follow. Here, a bar chart becomes a radial donut chart. By growing the wedges to take up the whole circle, we form a pie chart. We can also perform drill down operations, breaking up the data further into distinct categories. We can then unstack the bars to view the same data as a grouped bar chart. Of course, we can always reverse the transitions to return to the view we started with. We might want to compare different variables in a scatter plot to look for correlations. Here, we keep the y-axis values the same as the bar chart, but use the x-axis to show a new variable. Animation is also helpful for showing transformations to the data. Here we show applying a base 10 log transform to the data. Both data and axes smoothly animate to show the results of the transform. Visual encoding such as shape, color, and size can be used to visualize additional data dimensions. To evaluate the use of animation in data graphics, we ran two controlled experiments. The first experiment asked users to follow two targets across an animated transition and click their final positions. To better test how animation affects memory, we masked the display after the transition by turning it black. We compared static transitions, direct transitions in which all items animate at once, and staged animations where movements were split up over time. Our results found significant benefits for animation and found that staged animations, which split up movements through staggering or separate stages, consistently improved accuracy. The one exception was for changes in a scatter plot, where two quick transitions in a row were more difficult to follow than one longer transition. The second experiment asked users to follow a single target undergoing a change of value and then estimate the percentage change. The timing of transitions was slightly longer to accommodate some more complicated transitions. For stacked bar charts and donut charts, we experimented with more aggressive staging that separated translational movements from changes of value. To separate translations and value changes while also avoiding occlusion required a number of animation stages. Our results again found significant benefits for animation. Change estimation using simple staged animations that separated axis scale changes from other changes performed better than direct animations that combined both. The more complicated transitions for stacked bars and donut charts provided no benefits, arguing that the complexity of aggressive staging may outweigh any benefits gained from doing one thing at a time. Overall, users significantly preferred animation over static transitions.
Okay, so this is the key point. These animated transitions, and particularly staged animations, the last slide is the key point, is usually beneficial, but that's not universally true, right? There are limits to that when your animation simply gets too complex for people to follow. So yeah, what are the caveats? We already mentioned that changes can be hard to track, and we also have this eyes over memory principle, right? These temporal transitions, they are good, but we can always ask whether we can not show the two different stages or these multiple different stages at the same time.
Just out of curiosity, what's a donut chart used for?
A donut chart is like a pie chart. It's just proportional. Like part of the whole relationships, like your market share compared to your competitors and so on. It works just as a bar chart, as a pie chart.
So why do people use donut chart? Why don't we just use pie chart?
That's a design choice, aesthetic mainly. They are shown to be just as effective, and so yeah, it's not really a strong reason. Like visually, I think they're kind of more appealing than a standard pie chart because the inner segments are kind of tiny anyways. Okay, we can also use interaction to navigate. This is especially important when we have large spatial data sets. And the typical large spatial data set that everybody is thinking about right now is of course a map. So I want to be able to go to Google Maps, and then zoom in from a place. Like this is not a perspective that is particularly helpful if I want to find the president's office, right? So I rather want to be able to zoom in and then like pan and find the right location here dynamically. These things are also pretty important if you do proper spatial data visualization. Like here we have a brain or the pathways in the brain of a human as we have from an MRI. And so here I'm rotating, I'm zooming and panning, and this is this direct manipulation approach to rotation. But I can also use I can also use these specific staged approaches. Well, this one doesn't actually implement this that well. So yeah, zooming, navigation, panning, and so navigation, panning, zooming, and rotating is especially important in large spatial data sets, but also if I have like a large list-based interface, as we've seen earlier, when I need to scroll down. Some of you might have seen these scrolly telling techniques. This is essentially just like a different way of interacting with interactive visualizations. There's actually a research paper by a student in our group that kind of evaluated the benefits of scrolly telling. But before I talk too much, maybe let's just look at it and an example. Oh, I don't have an example here. It's not linked. Oh yes. So this is an example where essentially by scrolling, I'm telling the story, and suddenly I have separated, you can see that the scroll bar still moves, but it suddenly has a different meaning. It doesn't move the canvas anymore, but instead it breaks up these yearly plots into monthly plots. And then we change data, we change perspectives with animated transitions based on how I'm scrolling. So can anybody think about, is this always great? Is this always a problem? What could be pros and cons of using an approach like this?
What if, for example, the story is too long to be scrolled? You'd rather just sit and play it and just watch it happen instead? Yeah,
that is a possibility. Of course, if you scrolly tell it, you have control over your timing, right? You can go faster or slower, which you don't have if you autoplay it. So one problem that scrolly telling has is that it kind of hijacks a user interface paradigm that we usually are used to be something else. Like here, scrolling means, we are used to scrolling meaning that we move to a page lower down, right? And so if you excessively hijack people scrolling, this will lead to disorientation. Another problem is that is not always obvious, is like, where are you in a story? That is not quite as evident. They did a good job here by actually adding these little buttons here, and I can jump to any of those directly. But many storytelling interfaces don't actually do that. And so if you use, for example, a stepper instead, that could be a good approach. Yeah, and storytelling can also lead to unexpected behavior. So generally, I think this is a nice user interface paradigm that makes it also like one big benefit of, like, and I think where this mainly came from was by mobile interfaces, because it's just easy to keep swiping on a mobile interface. But generally, there is a couple of caveats that they have to be aware of. Here's another good storytelling example on what is warming the world, but I think in the interest of time, I'm going to skip over that. Semantic zooming. Semantic zooming is this idea that depending on a zoom level, that I can dynamically change a representation. So here's an illustration for how this is used in general user interfaces.
Hello, my name is Adam Barlow. I'm a program manager on the Windows Developer Experience team. Today, I would like to introduce you to the Semantic Zoom control, which is included as part of the Windows library for JavaScript. Semantic Zoom is a control used by apps in Windows 8 for displaying large sets of content in a truly user-friendly format. Semantic Zoom is unique in that it provides an easy-to-navigate, touch-optimized view of the data you present to users. In designing Windows 8, we wanted to ensure users wouldn't have to pan tediously through large sets of content with touch. Semantic Zoom is our solution to this problem. It gives users the capability of quickly jumping to sections of the view and greatly reduces some of the pain points traditionally associated with large collections. As you can see here, Semantic Zoom allows the user to quickly jump to any given location in the view, in this case, the last group of my start screen. Not only is Semantic Zoom a great navigation mechanism, but it also allows you to communicate a higher level of organization to your data, using the zoomed out or semantic view. For example, in the People app, you can zoom out. Here you will see a higher level abstraction of the data in terms of letters of the alphabet. This is extremely powerful and can be used to communicate important information to the users of your application. For instance, you can use the cell-spanning functionality of the WinJS list view to demonstrate the relative sizes of your groups. Although Semantic Zoom is easily performed with touch using the pinch and stretch gestures, it also works well with mouse and keyboard, ensuring that regardless of input mechanism, your users will have access to the important benefits of both the jumping and presentation functionality. With mouse, you can use the Semantic Zoom.
So everybody sees that the icons here are changing, showing more details when you zoom in.
You can zoom by holding down the control key.
Okay, in visualization we can use this to, for example, reveal more information about an item in a cell if we have more space. And so here's an example of that.
LiveRack, interactive visual exploration of system management time series data. We show LiveRack, a visualization system for viewing large quantities of time series data in the domain of system management. Monitored devices are represented by rows. This label shows aggregate information about a group, NFS, with 4 devices. Columns show one or many parameters collected from the devices. This column shows CPU usage. In the current overview, each cell is a small colored block. In these 4 cells, green means CPU utilization is above 35%. As I make the cells larger, labels for the individual devices become visible. Also, when the cells get big enough, the server is queried for more data, and then the representation changes from blocks to spark lines. Making a cell even bigger results in semantic zooming to show a more detailed line graph. We can see the current time range by looking at the time boxes. To the bottom left.
So notice how this started out as a color code of an aggregate information. Then by zooming in, suddenly labels appeared. By zooming further in, a tiny, tiny spark line without axis appeared. And by zooming further in, they now show axis, including a crosshair to interact with this very specifically. As a related technique is focus and context. In focus and context, we kind of like usually have an analysis focus where we carefully pick what to show and then hint at everything else that we are not showing. This is a kind of a synthesis of visual encoding and interaction, where the user first selects a region of interest, which is like then the focus, through either navigation or selection, and then we provide context through aggregation, reduction, or layering. And so this is like what these different focus and context methods are. There is this data elision or eliding data. So we have an overview list of items here, and then for selected items we show focus information. We can superimpose layers, or we can distort. Like here we provide green would be the focus, and then the gray bars would be the context. Or we can distort the geometry to put things in the center in the focus. And now we'll be talking about those in a little bit more detail. If you're not a native speaker, you might not know that word elision. I didn't know it until I learned about it in the context of visualization. This is the omission of sounds or syllables when speaking. So for example, as I'm in instead of I am in. And so this is also kind of the context as we use it in visualization. And so here is an example in the space tree, which is like a historical visualization technique. So we have focus elements, and then we provide context. We kind of indicate that there is more elements, and we can kind of elide them here and show these additional elements. This degree of interest is an important concept that is also a favorite exam question. Degree of interest is that we, this is like a general concept where we define that we have something that we care about a lot, and then other things that we don't care as much about. And degree of interest captures this in two terms. There is this a priori interests, and then the distance. So let me give you an example. If you look at, if you were to visualize cities around the world, you would probably like pick really big, important cities like London, New York, Paris, Los Angeles, Shanghai, and so on, to always visualize those. So those cities have a high a priori interest because they're important to many people. But if you're living in Salt Lake City, maybe like you are local here, and so you have like a very low distance to Salt Lake City and other cities around that. So for you, maybe it is pretty interesting to also see Provo on the map. And so this is kind of like what this formula does. So the degree of interest of each item is a combination of the a priori interest and the distance to your current selection, to your current focus. So like cities, generally there's this a priori interest of mega cities around the world, and then there is what is my current selection, what is my current interest, my current focus, and if it is Salt Lake City, then maybe these cities surrounding that should be the most important thing. And so this actually shouldn't be a minus, this should be a plus. So again, like a degree of interest is a combination of the importance of an item and the distance of my current selection. And so that has applications, pretty wide applications. The classical application that people use it in visualization for are things like degree of interest trees when you have hierarchical data. So here is an example where you can see that like main elements along the tree always remain visible, and like important categories, subcategories retain visible, but as soon as I go deeper, I see more information about these sub-trees. And so you can see like that these highlight categories, they always remain in the view. And so there's many different applications for this. It doesn't have to be like a hierarchical data set, although the hierarchical data sets are usually given as an example. Superimposition is when I have a focus layer which is limited to a local region of view instead of stretching across the entire view. And the best example for superimposition is this magic lenses. And the magic lenses...
Welcome everyone. I'm Manish Agrawala, a professor here in computer science at UC Berkeley. And
autoplay on YouTube. Okay, magic lenses show details of different data depending on where I move the lens. And this is like a historic video of magic lenses being introduced in an like interior design context.
Use two hands in concert to enhance our... It is equipped with a mouse for the user's dominant hand and a trackball plus thumb wheel for the user's other hand. This region of the screen contains a simple window system that we will use to demonstrate two new user interface techniques, tool glass and magic lenses. Tool glass is a movable, transparent... Another one. I have a symmetrical magnification with this slider, increasing by the appearance of the other. Tool glass sheets can include magic lenses, visual filters that modify the appearance of the objects beneath them. For example, this lens magnifies the objects underneath. We control the magnification with this slider, increasing or decreasing. This second lens is a filter that shows only red objects.
So this is the important idea here. This doesn't have to be a geometric filter, right? This could be any kind of filter that you apply. And so here, the filter is not geometric, but it filters out everything that is not red.
There's their effects. When we place the magnifier lens over the red object lens, we see that this little red object is a Time magazine.
Okay. And so here is a more recent example. It shows that pretty well.
In this video, the User Interface and Software Engineering Group at the University of Magdeburg, Germany is demonstrating a set of novel navigation. This example, users can zoom and pan through large pictures by performing multi-touch gestures on a table surface. In the following, we show how this task can be accomplished in a more natural way. For this purpose, we developed a paper-based mobile display that users can freely move through the physical space above the tabletop. This magic lens works as a magnifying glass to zoom in on an image by simply lifting or lowering the lens. At the same time, moving the display horizontally results in a panning operation. In order to help users maintaining the context, a circular contour line is projected onto the table display. The technical setup of our system is simple. The images on the lens display are generated by a projector and an infrared camera above the table. It works because the mobile lens
I'll skip over this. Okay, more about
the layered information space is a set of two-dimensional data, with each data layer representing a unique feature of a contextual model. In our example, medical students can study different systems of the human body. By lifting or lowering the lens, they can choose between the skeletal, muscular, blood, and nervous system. At the same time, a single layer can be explored by moving the lens horizontally.
Okay.
More.
You can also use these magic lenses to reveal conflicts. Like for example, here we're looking at flights into Toronto, and as you can see, all of the labels here are occluded. And by hovering a lens over that, you can distort these edges and then show the labels beneath them. Another way of using a magic lens would be to show all of the labels in, for example, a scatter plot, as we see here. Like this, the circle here is the magic lens, and by moving that circle around, the labels for all of the dots that are inside that circle are shown. The next important technique is distortion. And here distortion uses a geometric distortion of the contextual regions to make room for the details in the focus region. And so this is also another historic example. This came out from Xerox PARC by Jock McInlay in '91. And the idea here was to have a kind of like a spatial perspective to show how temporally they change data items. So this is like, you can think of this as like a time machine. When did I modify any of those files according to these different file types? and again, by kind of like distorting it back here, we get a sense of like, okay, there's a lot of items here, but there's not so many items here, without actually having to see all of those items. Another example are these fisheye views, where I can apply a lens and then distort a geometry. And these are just more like conceptual sketches. Here is a practical example for that.
Of Xerox PARC, containing over 300 nodes. The root of the tree is at the center of the circle, and successive levels of the tree are closer and closer to the edge of the circle. The edge is kind of like a vanishing point. Spacing gets smaller and smaller as nodes approach the edge, but the entire tree is displayed inside the circle. The structure of the tree is prominent, even when some nodes are too small to display text. For example, staff positions can be distinguished from line positions. By clicking on a node, we bring it into the focus area. Thus, we can see more of the detail in that part of the org chart, while maintaining the context of the whole. We can also grab a point into space and drag it around as we like. To achieve crisp dragging, and to keep transitions under 1 second, rendering of the tree is degraded in a couple of ways. Notice that the arcs are turned into straight lines, and less of the exponential fringe is painted.
So the idea here is that we have, and this is very similar to the degree of interest idea, right? Where you have like a focus region, and you see that in detail, and then you provide everything else here in context. You could also do that with maps. You can actually do that with maps. Have you ever used anything like that?
Yeah.
Yeah? Who has used something like that? There's like a couple of people who have done that. And
I have a question on the fisheye. Where is this used? How can one use a fisheye?
How can one use it?
Like, what's the use of using this?
Yeah, I want to start a discussion about this in a second, if you don't mind me giving one more example here. So here is an example of where supposedly you can see.
It is possible to monitor the activity of bus is a challenge for visualization. Possible to monitor the activity of buses throughout Singapore, but considering the large volume of information, exploring individual bus stops is a challenge for visualization. In order to achieve this, an interactive tool has been developed. It acts like a magnifying glass, allowing you to explore with great detail the activity of the bus network in Singapore. This magnifying glass distorts points in space to accommodate great zoom levels. It permits local browsing of the space.
So everybody would probably agree that this looks pretty cool and this is a pretty neat animation and so on. But then, what are problems that are associated with interfaces like this? I'm going to skip over this. What do you think about using distortion in that way? What are potential problems, and is it something that we can really rely on?
It seems like you kind of sacrifice this spatial awareness of things around what you're looking at. But you don't want to know what's the neighbor of what I'm looking at, and you lose all the information by distorting.
Yeah. That's a big problem there. Anybody notice any differences in these implementations? I think that this example with the bus network here is especially radical because they seem to almost have an extremely strong gradient between a zoom area and everything that is outside of the zoom area, right? So we can see that there's a ton of bus stops around here, and we don't really understand anymore how they're connected to what is in the zoom because everything is crammed down here. Whereas in this example here, it is a little bit more gentle. Also a little bit less helpful maybe if I want to see the details. And so I guess these examples are still, here are example of looking at linear lists like that. And these are still sometimes useful, but in practice I guess the consensus in the scientific community has emerged that these distortions have a lot of problems and therefore are only usable in very specific and narrow scenarios. So they're unsuitable for relative spatial judgments. As we see, we have the mental overhead of tracking the distortion. We have to somehow visually communicate the distortion that is going on. We have to show grid lines to give people an idea of how strongly this is distorted. Then we have this target acquisition problem. So if I want to select a specific location and I move my lens towards it, it moves around, and so it's not that easy to actually hit it. And so the kind of the results that people have had is kind of mixed in terms of how effective of a technique, a focus and context technique is this compared to separate views and even temporal navigation. This is an interesting example that I enjoy a lot, just for how neat the idea is. Who's read Calvin and Hobbes and knows what transmogrification is? So the idea is in this comic strip that Calvin, who is this kid, has a transmogrifier, and he steps into his cardboard box and then is transmogrified into a fantasy, whatever, dinosaur or whatever he prefers to be. And they actually pick up this term to transmogrify various different things. So they select something by tracing it, and then they extract it and show a linear representation of it. And now it's a circular representation. So here's how you could use something like that to even convert geometric objects like pie charts into or tree maps or icicle plots in this case into other representations. Like here we're transforming an icicle plot into a radial layout. I'll talk more about these techniques some other time. And this is all image-only operations, right? There is no understanding of these geometries in the back end. And so here's this rose and petal plot, and they're extracting this in image space to a bar chart. And then you could trace like a river, for example, and show the river straight and then everything else close to it. So this is pretty neat, and I really like the implementation, but I would also say that the application scenarios are somewhat limited. Okay, that's certainly not the case for filtering and dynamic querying. These are kind of like the key interaction techniques that we use in visualization. And this guy here is Ben Schneiderman. He's kind of like one of the forefathers of information visualization, and he's also a very, very prominent figure in HCI. And he, like his like many of the things that you've seen are based on his work. And he has published this interaction mantra that says, overview first, zoom and filter, then details on demand. And this is how he argues that people interact with many visualization systems. So first show an overview, for example, show you the whole map of the world, then zoom and filter, see, like for example, zoom into Salt Lake City, and then provide details on like the address of a location on demand. He also like includes relate, history, and extract, but I'm gonna look over those for now. And so this is a little tricky because I was planning a 20-minute exercise on this with 9 minutes to go. But anyways, I'll just show you this video. This is like dynamic queries historically. You probably notice as faceted search. So in an Amazon, for example, I can, like if I want to select a new television, I can say 33 to 43 inches, and then I can say I definitely want a 4K, and then I can say well, it must be from 2016. This is this faceted search approach. But you can think of this a little bit more dynamic, and historically, like we call these dynamic queries, and here's a good video
Again, the principle is to
of Ben Schneiderman himself introducing his home finder tool.
visually demonstrate the query components and the results and provide rapid and immediate feedback. For that, I'll take a look at the demo here on this display. Just move over to the side here, and we see on it a map of the Washington, D.C. area with the Potomac here. And this is an improved version of where we were a year ago in terms of dynamic home finder. The scenario I present to you is that we're coming up on a new administration, and you've taken a job with the Clinton administration, and your spouse is going to be working at the University of Maryland. You're looking for a home. So the first thing to do is to mark where you want to work here at the University of Maryland, right about, let's say, there, the A marker. And then your spouse is going to work downtown in the executive office building, right about over there. There's the B marker. Okay. And now each of these points of light on the display represent a home for sale. And if I move to the right, I can control this display by choosing the distance that I want to be from point A, and now it's set at 30 miles, and I'm going to bring it down, and you can control rapidly, incrementally, and reversibly the distance that you wish to be from point A. So let's say you decide, you see there's plenty of them, so you say you want to be, let's say, 5 miles from work, so that you could, let's say, bike to work. And now you want to be somewhere inside that range from B, so you slide down, and we now can see the set. And this is, looks like we've got 40 or 50 homes over there. If I now choose about the number of bedrooms, I really want 3 or 4 bedrooms, so I move this double box slider to be 3 or 4. I've still got about 30 houses on the display. So why don't we look at the price now, and we want to keep the price down, let's say about 170,000, between 140 and 170,000. And that's given us a set of about a dozen here. We could trim a little further by choosing.
So you get the idea. It's, don't think you'll find a $130,000 home in Washington, D.C. anymore, but essentially by dynamically adjusting query parameters, you can interactively and reversibly see the effect that these queries have. And next time, I'm not done quite, but I'll just tell you what we'll do next time. Next time we'll do an exercise of redesigning this interface for a special use case. So I'll be quickly showing those 2 minutes again. I think we need about 15 or 20 minutes for that exercise, and so it doesn't really make sense for me to do it now. So I'll skip over this. Just give you another example of these visual queries here. So here we've seen these parallel coordinates plots, but here, like, I have a direct manipulation interface, and that is kind of different from what we had before, right? Because the home finder example, we had widgets on the side, but here we are directly identifying the regions that we care about for highlighting. So this is a little bit of a different design, but it is the same principal idea of filtering based on dynamic queries. And we can have these kinds of queries in many different ways. So here is like a line plot, and then you can have like a rectangle query. You can have an OR condition on these, or an AND condition. Only the lines that match both of those rectangles are the result of your query, and so on. You could do this also for volumetric data. So here we have neural pathways, and this tool allows you to do these dynamic queries directly in this three-dimensional space. So you start out with, let's say, I only care for the path that runs through this lower part, like probably connects to the spine here, and then only those connections that run through that area are still remain in the view. And then I could say, oh, I really care only about those two areas that or the pathways that run through those two areas, and you could do that like that. A similar approach is incremental text search. We have seen this baby named Wizard, where we kind of like have a dynamic query by partial matching of and dynamic refinement of an input field. Or I could do like these explicit query interfaces, and I'm gonna skip over that. And I'll just close here, and then I'll talk more on filters after full break when we talk about views. And we'll do the exercise next time at the beginning, and then we'll continue on talking about designing visualizations and tasks. And on Tuesday, we'll be having the last T3 lecture before full break. Okay, I'll see you all next week.